good. Okay, so it's great pleasure to have Su Lee from Yao Center, and he's gonna tell us about one of the most important talk in 21st century. Open closed topological B model via large N.
Okay, thank you very much for the invitation. Yeah, like after Satoshi asked me to give a talk, I was thinking about what to talk about. I was thinking like probably I should give a talk on the physics content of the story. Actually, this kind of thing has two sides. I mean, like both physics and math have different flavor. I try to see how much I can explain. Yeah, this is about open closed topological B model. I mean, I say large N, I'll explain what I mean by large N. And so let me start with a little bit about its motivation. This was to understand the following phenomenon that I learned a lot from physics, and especially about this gauge gravity duality stuff. Like if you study this gauge theory at large N, I mean, somehow you can get the dynamics of the gravity. Well, for a while I was trying to understand how much, I mean, the content of this direction, and how much I can understand from at least the mathematical perspective, and especially in the topological sectors that I probably is the first step, like easier. So, so today I will try to explain a little bit about this phenomenon in this topological string, in particular in this B-twisted topological string. And here, somehow this model has a very nice string field theory description, and open string as a gauge theory description in terms of holomorphic Chern Simons, and the closed string has a gravitational sector by Kodaira-Spencer Gravity. So I will try to explain at least a bit of this perspective from the methods of homological algebras and deformation theory, and its deformation theory from the large M technique. So this is joint work with Kevin Costello based on two papers on the archive. This is the number. By the way, this is this one is a review work summarizing the paper stuff and also some content on the type 1 case. This is about original formulation of this open-close coupling. So let me start with a little bit description about this string field theory. So we know this holomorphic Chern Simons theory is the open string field theory of the B model topological string. Sorry. And in this talk, I explained the construction of this Kodaira-Spencer theory coupled to this holomorphic Chern Simons in the large N limit. And mathematically, this is a way to understand its open-closed B model, but on the other hand, it's also physically interesting, I feel. So this Kodaira-Spencer Gravity is this B model topological string, closed string field theory on the Calabl-Yau manifolds. And it was studied before, I mean, proposed by Prochaska, Sokori, Oguri-Vaffai around 1994 as a famous BCOE theory, like the B-twisted topological closed string field theory on Calabl-Yau threefolds is described by so-called Kodaira-Spencer gauge gravity. It's a gauge theory on the Calabl-Yau threefolds where fields are given by polyvector fields. And classically, they describe deformation of complex structures. And with Costello, we try to understand this theory and how to quantize, I mean, geometrically. So we find an extension of this Kodaira-Spencer gravity in the sense of a Zivabak, and it formulated of uptree Calabl-Yau with gravitational descendants. So I will try to explain our formulation from this perspective and how this is related to the open string stuff. So I will try to explain. Let me first explain this our setup. So the fields are given by these polyvector fields on Calabl-Yau manifolds. So we consider a Calabl-Yau. This omega x is the holomorphic volume form. And then let's denote this poly V to be these polyvector fields on Calabl-Yau. So this is like the book complex valued in this exterior algebra of the holomorphic tangent vectors. And this is all smooth vectors. And this space is a very classical example of DGBV algebra, where you have a nice differential, this double differential D bar, and also a BV operator, del operator, which is the divergence operator with respect to the Calabl-Yau volume form. And then the following BV relation holds, which is the famous BTT lemma. I mean, if you compute this divergence on the wedge of two polyvectors, you get this relation. And this, the bracket is the Shawkin-Nyrenhaus bracket. And this is a very natural example of this type of algebra. Now, that's the field content by polyvectors, and the full field of this Kodaira-Spencer gravity that we proposed in this generality is given by the following data. It's a polyvector field with one more formal variable u, and this u actually played a role of like a gravitational descendants. I mean, as we will see, and differential is the natural one, v bar plus u del, and the equation motion is given by the Mori-Cardan equation, like this type. But here, this mu is an arbitrary element in this space. So it's very big, there's many components, U components, so it's a very big equation. I mean, you can decompose this equation in terms of different orders in U. And roughly speaking, this equation describes extended deformation of the pair. So it's about the Calabl-Yau deformation, not only complex structures, but also deformation of the Calabl-Yau volume form. And you can think about this this parameter as parameterizing something on the vacuum line bundle. And this is the gravitational theory describing the fluctuations of a Richard flood matrix in terms of the complex structures and also Calabl-Yau volume forms by the famous Calabl-Conjecture-Yau theorem.
So I have one question.
Yes.
So what's this bracket sub Sn mean?
Oh, this is a Nyrenhaus bracket. For example, when mu is the usual, so here, when this mu is the usual vector field, that's the vector field for the algebra.
I see.
So, yeah, but for polyvector field, it is also generalized.
I see.
So,
I see.
So it's an analog of this the bracket for vector fields, but for polyvector.
Oh, I see.
But this is a Calabl-Yau complex manifold, so it's a holomorphic part of this data.
Okay, thank you.
Yeah, that's roughly speaking what it says. And the point here is like this equation describes the deformation problem for complex structures, and also Calabl-Yau if you encode this U parameter. Now on the space, that's the field content, but on the space there's an interesting dynamics. So the classical theory of this model is described by a degenerate odd Poisson structure. So let me try to explain what this means. Actually, this is a little bit subtle. So let's look at all the possible local functionals, or local, on our space of fields. So remember, this is a very big field, has infinite many components. So usually a local means like this action is given by an integration from local density. So L is like branching density. And so U is very big. It has many components like mu0, mu1, etc. Depends on which order is in U. Now, for any kind of such a local functional, we can define a degenerate BV anti-bracket on this space by the following formula. So this is like a intuitive formula. It can be very precise. So basically, if you look at the bracket of two local functionals of this type, so you do a variation for one of the mu0 components. So that's only the 0 component, no other fields. So and the same thing for S2. And after you do variation, you apply a del operator, holomorphic del operator, and then do integral. That's another local functional. And that's you can show this defines the anti-bracket, the BV anti-bracket in degree 1 and odd. And I would say, I mean, I want to emphasize like this anti-bracket only involves mu0, so it's highly degenerate. And actually, people who are familiar with integrable hierarchies will see this Poisson structure appeared in this KDV and many other cases. And there's it's not a coincidence. Actually, there's a hidden KDV type integrable hierarchy like in this story. Now, so with this bracket, you can find a solution, so-called classical mass equation. It's given by the following, like, so this is standard story. We look at the so-called gauge theory in the BV formalism. You have an anti-bracket, you have some data, then you look at so-called classical BV mass equation of this type. Now we have a differential Q and the bracket, and this look like a Mori-Cartan equation, but this bracket is degree 1. And it turns out like this one, I mean, in terms of this particular degenerate Poisson bracket, you find a natural solution in the following way. So this describes the classical dynamics. So it's captured by the following action functional. I call this one I0. And again, this is local functional on our space of fields. So Polyvector Fields with descendant U. And here I use like a bracket 0. And this means the following. Like, so first you'll do like a power series expansion for e to the mu. So for example, like a mu to the n, or n factorial. And for each n, n tensors of u, this bracket 0 means the following. Like you do basically psi class intersections and you get some coefficient. And so I guess people who are familiar with coordination theory find like this is like a psi class intersection on the modular space of pointed rational curves. And for the polyvectors, you take the wedge and you integrate. And actually the formula also was found in the, actually Andre also found this formula in his description of this Hodge field theory. Intuitively, what this one, I mean, the way we get this formula is like we look at this B model, and we know this like topological B model localized around constant maps. And if you study the modular space, and that's roughly speaking the effective theory locally around these constant maps. And what's essential is the following: like, whenever you find a solution of like this classical mass equation, I mean, this is equivalent to describe an L infinity structure on the space of field, I mean shifted. And in this case, the corresponding L infinity structure is given by the following. Like this is a cohomological vector field where L1 is Q. That's the differential d bar plus u del. By the way, you look at the d bar plus u del, I mean, that's the splitting of the drum to like Hodge piece. And that's a typical situation for B model. And you can look at higher brackets. And higher brackets come from looking at how what is the result of bracketing with the classical functional using this degenerate BV degenerate Poisson bracket, and you find the following formula. I mean, if you look at n inputs, the higher bracket produce an element of the following type. So the output contains no descendants, and if you basically you put a bunch of mu's wedge and take the divergence operator with some coefficient. And that's the same expression by understanding bracket with I0. So you see, like in particular, if you look at I2, I mean L2, for example, is a bracket, and this bracket is only non-managing on like u to the 0, no descendants, and you take two elements, mu1, mu2, it goes to del of mu1 wedge mu2. And essentially, it could be complicated. And this sounds very unnatural because in the beginning, I mentioned that this B model, the classical geometry of B model, is described by the Mori-Cartan equation of the DGLA, like this Q and the Sheldon bracket. So actually, these two structures are quasi-isomorphic. They are L infinity quasi-isomorphic. And this actually is the mystery part. So you look at this complicated L infinity, and you look at a simple, this DGLA, and they are related by the period map. And the role of the period map connects to L infinity structure. It's given by the following: like you start with an element of the mu of the sigma, our fields, and you look at this expression. So E to the sigma over U is the natural expression for like a period map for like deforming this volume. And this is like about this dilatation shift and so on. And you look at the plus means like you truncate to all the non-negative powers in U and look at this expression. I mean, at first order, it's the same thing as sigma. You can see like if you expand it, the first order is sigma. We have all the higher orders, and this is a highly nonlinear map. And this highly nonlinear map interturns this L infinity structure that I mentioned, which is more natural from the string field theory point of view, to this particular simple DJLA, which is more natural from geometric point of view. And that is the period map. After you find this, then, I mean, that's basically you describe all the classical story. Now the next thing you do is to understand how to quantize. And there's a standard way of doing this. I mean, is like a usual so-called BV formalism. So start with a solution of classical mass equation. I mean, to quantize the amount to find a quantum corrected local functional. I mean, they intuitively, I mean, naively this is local, but later on, when you normalize and so on, you get non-local stuff. But I mean, ideally, like you start with a classical solution, I not, then you deform by adding two H bar components to your original action functional, and try to claim that this is gonna solve the quantum mass equation, like Q plus H bar del plus bracket equals 0. And you can see like if you set H bar goes to 0, this quantum mass equation becomes the classical mass equation that we described before. And this is how we quantize. And basically, one way to say this, to understand this equation is about this quantum consistent condition. So eventually, we're going to use this one as our action functional to integrate over, for example, a so-called super Lagrangian in our space of field. That's a gauge fixing condition. And this property would ensure that it doesn't depend on the change of the gauge fixing. That's the gauge consistent condition at the quantum level. So that's the kind of equation we want to solve. Now this delta C, let me say a few words. Like this delta C is the BV operator associated to the shifted Poisson structure. So remember, we have an like odd Poisson bracket. And if you look at the integral kernel of this Poisson bracket, you can use this one to build up an order 2 differential operator on our space of field, functions on the space of field. That's gonna be defining this BV operator. But the point here is like, because we're working with infinite dimensional space, this Polyvector field is infinite dimensional, and the bracket is local. You see like the bracket, the kernel function for the bracket, it looks like a delta function. And the BV operator is EO defined. So it suffers from the so-called, the famous EUV divergence. So intuitively, I mean, you want this equation, but it's not directly defined, well-defined mathematically. I mean, physically, that's something we would like to solve. So there are a bunch of ways to understand this equation. You have to regularize and look at the renormalize the version of this equation and solve it. And possibly you're gonna have anomalies and so on. And we'll see how this works in our story. I mean, open close story later. We can how this is generalized. But indeed, the anomaly plays an essential role. I will try to explain the anomaly later. So that's the kind of thing. So in our approach, we use a particular way to renormalize this equation to make it well defined, at least rigorously. We use this method developed by Kevin Costello. I call this one like a homotopic renormalization. The idea is like this. I mean, originally, if you don't do anything renormalized at the original point, you find equations of EO defined, you find this UV divergence, and so on. So you regularize this a little bit, go to a nearby point, and you can define these BV structures there and try to solve quantum mass equation. You might find anomalies, but you can, at least this equation is well posed there. Then to see how this depends on the regularization, I mean, go to another point. You look at also a BV structure there and try to solve. And then you will see like if you go to different points, they're related to each other by this a version of a like RG flow type equation. I mean, we're gonna call this one homotopic RG. It's different from the flow of the rescaling, the physical RG, but this is an RG connecting different regularizations in this whole picture. Then once you can do understand this picture, you understand all the nearby points. Then this is a definition of the original point on a yield-defined point. And this is very similar to this, for example, the construction of residues in algebraic geometry. So we know this, you have a very singular point. If you want to define the residue, you can deform it to a bunch of like non-degenerate singularities and take the residues here and show it doesn't depend on the deformation and so on. And so here, like it doesn't depend on the deformation up to homotopy, and you can still formulate the theory. And that's roughly speaking the idea. So once you can solve this quantum mass equation, then you can obtain a generating function on the cohomology. That's the cohomology of the space of fields. And usually, like if you look at the physics literature, the corresponding states in the B model is given by the cohomology of the Polyvector field. And they are related by a choice of the splitting of the Hodge filtration. So this is a particular, choice, and you may go to different choice if you go to different points around this moduli space. If you go to large complex limit, a particular choice, but if you go to some other points like non-negligible points, you will find some different choice. And the change of the polarization will change the numbers. But you can describe them explicitly. So now then you collect the G-loop Feynman diagrams, roughly speaking, but you have to take into account all the quantum corrections. The way the corrected functionals and so on. Also take into account the renormalizations. Then this is a way to define this higher genus B model. And we actually, after you do this one with conjecture, like this is a mirror to the higher genus coordinate invariance in general. In the simplest example, for example, in the case of it curve, you can see this one explicitly and how this is related to this coordinate invariance. It turns out to be a consequence of like a Boson-Fermi correspondence. Also, in general, it depends on the choice of the splitting or the Hodge filtration along this moduli. It give rise to this famous holomorphic anomaly equation. And you can also visualize this stuff explicitly in some simple examples. And that's actually all I want to say about this closed string sector. And actually, that's a quick review on some previous works. But that's not the one I want to emphasize. I want to emphasize today about this open string sector, the gauge theory sector. So it's roughly speaking.
Let me make, sorry, yes. Let me, so you see the splitting, the Hodge splitting is also a piece of the data.
Yes.
So it should be better to put it inside the data of the theory, because before it's not well defined.
Yes, but the data. Yes, but the data actually is about this monodromy. So if you put this monodromy things into this theory, then it's part of the data. But actually, just one subtle thing I want to mention. So, for example, even in the quintic example or something like that, you have this large complex limit, and around there, you have a data fixed. But if you go to orbifold point or things like that, you have some different splitting. That's gonna this splitting. You can also formulate the story there around that point, and the splitting is gonna be different from the larger complex limit. So we can, for the particular theory, we can put this one into part of the data. But here, probably I was thinking about something more like this is one independent. Like on one side, you can formulate the stuff, but if you want to get numbers to get the invariance, then you put this one into part of the story and add into what we have and do this splitting and then get numbers. And probably this is another way of saying this. But yes, I agree. Yes, this part of the data. Yes. Okay. Now I want to talk about this open string, and the key point here I want to emphasize is the following: like, I want to start with open string as a gauge theory, and I want to see how I can recover all the dynamics of this Kodaira-Spencer gravity that I described before. this more Cardinal equation and this quantization, all this kind of complicated stuff. I mean, they're gonna be recovered from this open string data. And in some techniques, in deformation theory, in the large limit, that's the thing I want to explain. So, so the open string, as I mentioned in the beginning, like it's described by this holomorphic Chern Simons and as described by Witten. So now I want to describe its coupling with the Kodaira-Spencer gravity. That's going to be the crucial step. So let me first briefly recall the content of this holomorphic Chern Simons theory, which is the open string field theory in the beam model. So if you take a Calabl-Yau threefold X, and your G to be a Lie algebra, let's say with killing trace pairing trace, and the field content of this holomorphic Chern Simons is given by this guy. It's like a Debug complex valued in some Lie algebra, or you can have some bundles like Lie algebra bundles or some kind of principal bundles can have different content. But roughly, let me write in this way. And you have an action functional of the following type. So you look at A wedge d bar A and plus this expression. This expression is very similar to the ordering Chern Simons, but now this is like the Boole complex valued. So if you take this expression, you wedge with the holomorphic volume form, and you get a top form and you integrate on Calabl-Yau threefold, for example. And also like I work directly here with the so-called the master action for the holomorphic Chern Simons. The usual holomorphic Chern Simons is described by like say the 0-1 connection. So it's a 0-1 form and you have the same expression. But if you do this kind of gauge fixing procedure, you end up with such a master equation, a master action. So 0 form play the role of ghost, and the 2 form and 3 form play the role of like anti stuff. So again, one way to remember or understand this action is the following: like it gives rise to an BST transformation. If you think about this one as a variation on the space on our fields. So delta applied to A, it produces like a d bar A plus 1/2 A bracket A. And this equation has to be read in components. So because A has like a 0, 1, 2, 3 components, you have to compare both sides. For example, the 0 form part on the left-hand side, it match the 0 form part of the right-hand side. So it's a bracket of 2 0 form part. That's the ghost field. And the 0-1 form part is like d bar of the 0 form part plus the usual bracket, and you will find the usual gauge transformation. Again, like a del square is 0, it's a cohomological vector field. It's basically equivalent to saying that this d bar and the bracket forms a differential graded Lie algebra, and that's also a very standard formulation. And also, the locus of this transformation describe the classical equation motion. And here, geometrically, this equation motion describe a deformation of holomorphic vector bundles, and that's the geometric content of this holomorphic Chern Simons. So basically, the critical locus of this holomorphic Chern Simons describe the moduli of the holomorphic vector bundles, and that's the classical story. But this classical story already leads to a lot of interesting development, like Donaldson Thomas invariance and so on. But now that's not the thing I want to explain. I want to explain the deformation theory. So we know like the usual like topological, like the usual Chern Simons theory, which is topological, it's rather rigid. I mean, sort of like the only thing you can tune, I mean, in that theory is to tune the coupling constant. I mean, which so not much you can do. It's very topological, rigid. But if you look at holomorphic Chern Simons, this one has a huge degrees of freedom to deform while preserving gauge symmetry. So, so for example, the usual way to understand this one is the following: like if you start with the original action functional, and you deform it by another local functional, and you deform it in a way that you want to preserve. I mean, which one is like a preserve gauge symmetry, and because the gauge transformation is generated by this BRC operator, so this is the same thing as saying that this local functional is BRC closed, and that's the kind of thing we want to preserve. And also like you want to solve this deformation up to gauge equivalence. And again, at first order, it's a standard thing to say that this gauge equivalence is described by delta exact forms. So by looking at this kind of simple description, it's not hard to imagine that the first order deformation of this holomorphic Chern Simons is parameterized by the BRC cohomology, like just given by the cohomology of, this cohomology of all the possible local functionals by this BRC operator. And that's the kind of thing we want to compute. And as we will see, like this is very big. It's unlike the topological case. But on the other hand, if you observe like this differential, the delta, this gauge transformation, play the role of like a Chevalier-Ellenberg differential, then it's not hard to imagine like this amounts to compute some kind of Lie algebra cohomology. And that's indeed the case. So let me just tell you the basic idea, how this is computed. So usually, like if you want to compute Lie algebra cohomology, for abstract Lie algebra, it's very complicated. The generator is like you have a very large generators with non-trivial relations and so on. But the situation actually is greatly simplified if you work with large N. So let me explain this one by a simple example. Actually, there are a lot more to explore in this direction. So you can look at many other interesting gauge theories like a super Yang-Mills. There's some actually calculation for super Yang-Mills, some other examples and so on to look at how to recover this gravitational sector and possibly to recover this dynamics. But in our case, if you look at this simple example like a G by M by M matrix like GLN, and look at N to be very large, and you look at the deformation problem, and there's a very classical theorem which is called a theorem of Laudet, Quillen, Sigan, and which says the following: like if you try to compute the Lie algebra homology or cohomology at a larger limit, they compute it by like a polynomial rings of the shifted cyclic homology or cohomology of the corresponding ring, and that's a very like classical result in like homological algebra. So and intuitively, this is a cyclic homology or cyclic cohomology. This cyclic cohomology basically represents you insert a circle of operators and how to evaluate. And physically, it's not hard to see that like, this matched with the notion of single trace operators. So you put a bunch of trace and so on. And so, but in this expression, like you also look at like polynomials of this guy, and the higher like orders, like symmetric tensors of this guy, are basically representing these multi-trace operators. So this is a way to start with the data in the gauge theory, and go to large N, and you compute the Lie algebra cohomology, and it's the same thing as computing cyclic homology, and you get all the single trace operators and multi-trace operators, and that's roughly speaking the content of the theorem. And then it's not hard to imagine like this single trace operator are those operators like coupled to these gravitational sectors, and this is indeed the case. So let me try to explain what's happening in our example. So we can recover this Kodaira-Spencer gravity from this large N technique in the following way. So in our case, this algebra is given by this Debye complex. So remember, like we want to compute this and you can see like our algebra is given by the Debye complex valued in some Lie algebra. In our case, it's like M by M matrix. So that's the content of the holomorphic Chern Simons. So we want to compute this Lie algebra cohomology for this particular DGA, which is the on Calabl-Yau threefold. Then this can be computed. Well, actually, we want to compute a local version of this one. There's subtlety here that I didn't explain, but we want to compute a local version of this one as a local coupling. And one way to say this is like we want to compute some kind of the analog of an energy moment tensor with respect to the response to the deformation of the local stuff. So anyway, it's a standard classical result of like a HKR map, which computes this cohomology. It's computed by exactly the Polyvector fields with the descendants as described in the very beginning. So that's the field content of the Kodaira-Spencer gravity. So here you see, like you finally discovered the field, the Kodaira-Spencer gravity from this cohomology calculation, and by saying that this Kodaira-Spencer gravity is the first order deformation of Holomorphic Chern Simons at large M. And that's one way of understanding this statement. And so this is a very familiar statement from physics perspective. Like that's the usual thing, like coupled to the gravitational sectors, and by single trace operators. Well, that's the good starting point. But this is only the field content. I mean, usually, like we know, like in this story, like we compute the gravitational sectors, we compute so on, we match the fields and match some symmetries. But more non-trivially, like we want to match the dynamics, for example, how to recover this dynamics. And that's a different level of the story. But let's see. Before we do that, let me just give you some example on the deformation and on the coupling. So if you start with an polyvector, let's say K polyvector without descendants, say just like K polyvector, you can show like it couples to it gives rise to the following deformation of this Holomorphic Chern Simons. So by the following, like if A is given by like a connection, so you look at A wedge del A essential with K times of del A, it looks at mu contract with this guy. So you see like mu has K polyvectors, and here has K forms and contract everything. So another way of saying this is like, like there's a bunch of differentials, derivatives involved in this mu, and these derivatives act on this A's in such a way. And this defines a local functional, which is parameterized by this mu. That's a deformation, and this can be like this can be used to deform this Holomorphic Chern Simons. But actually, you can write down all the possible deformations. I mean, at least at first order, and actually, there's an explicit formula at this level. So we'll start with, for example, if you start with a polyvector with the descendants like u to the m, is m's descendant of the k polyvector. Then it gives rise to the first order deformation of the Holomorphic Chern Simons of the following type. Like say, it's just a complicated combinatorial coefficients are in front of this expression, but roughly speaking, it's given by a linear combination of the form. So it's a bunch of derivatives and some orders and so on. And this mu acts as a derivation acts on some of the connections. And this descendants represents the kind of orders, like say, for example, L1 to Lk sum up to 2m. M is the order for the descendants. And the general explicit formula can be described precisely by Virchow-Kalak's cyclic extension of consecutive formality. And this is not hard to imagine because, for example, in the B model, like if you look at this B model, it's analog, basically it's analog of this Poisson cycle model. And if you compute the disk amplitude, and this disk amplitude gives rise to this deformation of Holomorphic Chern Simons, and that's exactly concept graph formula. So that's why, I mean, you will end up with, I mean, you can, on the other hand, I mean, reversely, you can use concept formula to show such couple system solve a version of a classical mass equation in the couple system. And that's basically the content of conceptual formality, physical content. Now, so what we have now, I mean, so first we have this Holomorphic Chern Simons. And roughly speaking, this Holomorphic Chern Simons represents like a local interaction, I mean, disk amplitude. I mean, from the Virchow point of view. Then you look at the first order deformation. So you look at, again, an analog of disk amplitude here by inserting one bulk deformations. And you can write down the formula explicitly. And they can show, like, I mean, you have to require to satisfy a version of the quantum mass equation. But in general, we want to get quantum correlators on a Riemann surface of genus G. Now with a bunch of boundaries, where on the boundaries you insert this gauge fields. On the bulk, I mean, you insert these polyvectors. That's the closed string sector, and you get expression like that. So it's like IGH something with both open string and closed string sectors. And G is the genus, H is the number of boundaries, for example. That's a that's kind of thing we want to construct. And what is the principle for constructing this? I mean, again, we require it satisfy a quantum mass equation. And this is a quantum mass equation, I mean, described precisely by Feuerbach. I mean, it's open-closed BW mass equation. In his general description of open-closed string field theory. And the mass equation, roughly speaking, says like if you look at the degenerations of the Riemann surface of genus G with H boundaries, and all the possible degenerations give you expressions for how to write down the mass equation. And that's the shape of the equation given by these degenerations. So let me give you some example. This example of genus 0, H equals 1, so it's the disk level. On the disk level, if you apply BRC operator to this kind of disk amplitude, and becomes a degeneration and goes to the boundary, and the degeneration of this guy, I mean, has two possible contributions. First, you degenerate the open string sector, the disk, for example. You become two disks for a bubbling of the disk. Second, you can have a bubbling inside the bulk. So it's a bubbling of the sphere. And these two diagrams contribute to this disk amplitude. I mean, this boundary contribution of the disk amplitude. So just from this expression, you can write down the corresponding required equation. This raised as follows. The first one, Q. So this BRC operator applied to the disk amplitude, Q01. So it means like this is like a genus 0 with one cyclic tensors. And if you try to write down the local functional, and if you have to be equal to up to some size, the first term here represents a bracket in the open string sector. So this bracket O means like the BW bracket in the open string sector. The bracket C means the BW bracket in the closed string sector. You can write them down rather explicitly. Like for example, I explained this bracket C before, and bracket O is the bracket O coming from this Holomorphic Chern Simons that is also so-called a -1 shifted simplified structure that it can help you to write down this bracket. So this expression, 0,1, bracket 0,1, is the first diagram on the right-hand side. So it's a degeneration of the disk. Second one, the closed string bracket from an I01, so disk amplitude, with the I0,0, which is a pure closed string sector, is the second diagram on the right. So you see, like you look at the bubbling of the sphere, and this equation has to be satisfied. And by the way, this expression is essentially equivalent to conservative formality theorem. So, I mean, that's the content of this equation. But on the other hand, I want to mention, like, you see, this equation, the left-hand side, and the first diagram on the right-hand side is the open string information. Now, the second diagram, you see, like, the bubbling of the closed string sector. So you started to see some dynamics because you see, like, you have a BW bracket entering into the story. So it started to visualize this the dynamics in the closed string sector. So that's the first case. So here's another example. This example in the pure string closed string sector. So if you look at a genus 2 diagram without any boundary, so without open string sectors, and you look at the deformation, you can have this kind of nodes, and you can deform to, I mean, the degenerate to 2 like genus 1 curve, and you have a bubbling of the sphere. Then you can write down the equation in the following way. Like, say, if you look at a BRC operator applied to like a genus 2 like functional, it becomes the first one. This node actually becomes a BW operator, like connecting the point to itself. It's like a BW operator applied to a genus 1 diagram. And with this term, with the bracket of the 2 genus 1 diagram, and also with this like a bracket of the sphere with a genus 2 diagram. And that's roughly speaking the way to write down this expression. Now, this is another example. This example plays probably the most important role in this talk. It's an example where we're gonna help us to detect the anomaly cancellation condition. It's the following. Like it's the annulus diagram with genus 0, h equals 2. So it has two boundaries. It's annulus. So if you look at annulus, look at the degeneration, you can have a bubbling of the disk. And if you have this kind of one loop diagram from this gauge field, like open string gauge field, and you can have the degeneration like the gluing of two disks with closed string dynamics, and finally, it's a bubbling of the sphere on the annulus. That's all the possibilities. If you write down the equations, I mean, it becomes like a BRC operator applied to I 0,2. That's the genus 0 with two boundaries, equals or plus minus this I 0,1. That's the disk bracket with the I 0,2. That's the annulus, and this is because this is an open string bracket. So this only involves the open string bubbling. The second term is the self loop. I mean, it's a one loop diagram in the open string sector. So it's the BW operator applied to I 0,1. The third diagram is like a bracket. It's a closed string bracket of two disk amplitude. So that's roughly this diagram, what it look like. And finally, the bubbling of the sphere is again closed because it's not. You see, like it's still inside in the interior of the Riemann surface. So it's a closed string bracket of a sphere amplitude with annulus. And that's all. I mean, that's all the things we have. I mean, just to describe this equation. And as we see, like this equation is the one we're gonna it's the most difficult one to solve actually. There's a reason for this, because this open. If you look at the coupling of this open closed B model, and eventually it becomes similar. It becomes analog of a topological theory in the sense like we don't have much coupling constant to tune. It becomes topological. Any kind of dimension that like a parameter with dimensions will be like a homotopic trivial, and the dimension of the coupling is given by like 2g minus 2 plus m plus h. Roughly speaking, that's the counting we're gonna have. So this diagram contributes to like dimension 0. This diagram. So it's a dimensionless coupling constant that it might contribute to anomalies. And many other diagrams they have like a dimension, and the coupling constant have dimensions, so we can show by deformation theory they're gonna be homotopic trivial, so it can be solved directly automatically. But this diagram is the hardest to solve. And this is the kind of theorem. this is basically the kind of thing that I explained just now, but let me just say precisely in words. So if you look at the local piece of the Calabl-Yau, so on Cn, this is the local piece. This is a piece we're gonna try to understand this in particular this holographic stuff. So in Cn, actually the most interesting application for us is C5. It's like r-dimensional, 10-dimensional space-time. And this is gonna be the place where we try to understand a twist of this type 2B supergravity and see what we're gonna have. And we can conjecture like this gonna be equivalent to this kind of Kodaira-Spencer gravity on this 10-dimensional space. But anyway, if you start with such a data, and you start with like Holomorphic Chern Simons theory with a Lie algebra, the Lie algebra has to be taken into valued in the super Lie algebra like GLn/n, and this is very important. Like you have also n copies of the Fermion directions, so, GLn/n, and in this super Lie algebra, and also you start with the first order deformation by this Kodaira-Spencer gravity, and this can be computed explicitly. And I also explained what it looked like in some examples before. Then if you just start from these two data, there's a canonical way to quantize all this IGH to all the genus and boundaries, satisfying this open-closed B mass equation. And such quantization glues on any Calabl-Yau with non-trivial C-star action. So I mean, this doesn't apply to the so far yet applied to this compact case, but it's for this non-compact with C-star actions. I mean, that's a very nice story about this gluing. And this result can be viewed as a space-time analog of this UV finalities of string theory. I mean, this have a natural, like at least perturbed quantizations. I mean, it's renormalized at all orders, like in this way. And in particular, I want to mention, like you see, like the full dynamics of the quantum Kodaira-Spencer gravity are recovered by basically by looking at how they are involved in this quantum mass equation, how they're connected by solving. You see, like you already see, like the dynamics of the closed sector appeared in some terms of the mass equation. And by this consistency, I mean, by solving mass equations, you basically using deformation theory, they can be recovered explicitly. I mean, not explicitly, but I mean, some orders can be explicitly, but can be solved like at all orders. I mean, using deformation theory. That's the one way to rate the statement.
I have one question. Is the assumption X is Cn is important? So can you make it like any like arbitrary Calabl-Yau and so on?
The assumption on non-trivial C-star action is essential.
Okay, I see.
Yes, that's why I mean, but I mean, essential is technical essential. I mean, because this one was simplified anomaly calculation. But in general, we should expect like this could be formulated on arbitrary Calabl-Yau. But then in the gluing stuff, there's a highly nonlinear symmetries which will act on the space of anomalies. So that's the part which is most difficult to solve. That one we haven't completely solved yet. But with natural C-star action, then the anomaly, the action on the anomaly is linearized in a very simple way. Then you can basically just read off the dimensions of the coupling constant. Then you're done.
So when you say okay, go ahead.
So let me ask two questions. First, yes. What do you mean by gluing?
Yes. So basically, you require existence of Calabl-Yau volume form. Well, I just mean this. For example, you construct this one locally on a piece of the Calabl-Yau. Then you see like the transformation acts on the full quantization because this one is local. The issue here is like the B model is local on the target, at least at the UV limit. Then this local quantization can be glued. I mean, basically for the action functionals, local functional can be glued. But then you have to look at how such things are glued. For example, I guess you have something in mind to ask about this the diffeomorphism groups, how they act on the quantization. Such a thing will be quantized. And there's a normal, it's basically a cohomology which guarantees how such a thing can be transformed under these transformations. And if you look at
gluing mean by diffeomorphisms.
But this one is a diffeomorphism preserving Calabl-Yau structure. So locally it's like Calabl-Yau automorphisms.
Okay, so another second question. I see. So gluing from chart to chart, you mean this?
Yes.
Okay, so that's why second action. You see, if you have non-trivial C-star action, you can have a localization. Do we mean this in mind? Yes?
For this non-trivial C-star action, well, from this worship perspective, I guess that's one. Are you asking about this?
No, I'm asking, you say, I'm reading, such quantization glues on any Calabl-Yau with a non-trivial C-star action.
Yes.
So I assume you mean the C-star action on Calabl-Yau, right?
On Calabl-Yau, yes.
Yes, and if you have C-star action on Calabl-Yau, you can make localization.
You can make.
With respect.
Yes, but I don't. But localization, you mean localization for the sigma models, or from the. I don't precisely know the content of. For example, if you localize, if you want to do calculations for this couple system and using this localization, that's one possibility. I don't know the answer yet, but
so that's why I'm asking, because when I see Calabl-Yau with a non-trivial C-star action, I immediately turn on in my mind that if you have such a thing, it could be localized to the fixed points of this direction. And it makes life much simpler.
Yeah.
So is it what you mean?
Oh, we don't know the content of the localization. So for example, how this compatible with localization, I don't know. So you're right. I mean, so with this action, in principle, you should be able to derive more constraint data, like when things localize and look at, I mean, say, for example, originally we were working with like only a single copy, CN. That's a natural sister action. But then you have a bunch of points like CN glued with a sister action. Then probably you can localize to a particular 2 points and how they are related to, for example, analog of semi-simple stuff. I mean, this in principle can be studied, but we don't know the answer.
One comment at that point is if you study A model, not B model, but A model, and if you have a C star action, then you can easily show that you get a string field theory out of it. It's basically the work of Giventhal for 20, that was 25 years ago.
Yes.
So it would be nice to compare this, to compare his formulas with your formulas.
Yeah, I see. So that's
so it was just a comment. So please go on.
Okay, yeah, thank you. So I guess, yeah, that's a good suggestion. Like probably can be understood from the B model worship perspective. When you have this sister action, I guess it's gonna be compared with like A model perspective, the mapping space and localized and so on. Yeah, I try to think about it. Thank you. Okay. Now I want to say a few words about how such a thing is understood. I mean, basically we proved this one by deformation theory, but on the other hand, there's a lot of content inside this formulation. Originally, we want to apply this one to phi, as I mentioned, to understand type 2B supergravity and a particular holographic stuff. But here then we find something interesting, which is the analog of the Green-Schwarz anomaly cancellation stuff. I guess this is not a surprise because this is exactly doing similar string theory. So the way we construct this quantization is the following: like, if you start with the disk amplitude, I mean the Holomorphic Chern Simons, and with the first order deformation, like one bulk insertions, then you can formulate the deformation problem to reconstruct all the higher stuff by writing down the mass equation and solve order by order. And the order by order is in terms of the counting of the boundaries and the closed string insertions. And that's, roughly speaking, what is happening. And I mentioned just now, but I want to say again, like, there's a way to understand this amplitude by looking at the dimension of the coupling constant. If you have a sister action, it turns out this dimension is given by 2g minus 2 plus the number of boundaries plus the number of closed string insertions. So the whole theory is going to be topological, and it's not hard to imagine like only dimensionless stuff, the coupling constant, might contribute to the anomaly. That's the physical way of saying this, but you can prove this one directly using this deformation theory. So then you look at the dimensionless couplings, and there are only two possibilities. The only possibility is like a genus zero H genus 0 and H, the number of boundaries and plus the number of closed insertions equals 2. That's the only possibility for dimensionless coupling. And in our case, it means like a genus 0 with one boundary plus one closing insertion. But this is exactly the first order deformation of the problem. So this is basically known. So this data is this coupling is the dimensionless part coupling, which a priori might contribute to the anomaly, but they are constructed explicitly from the conservative formality. So this one is solved. Now the other one is the case where you don't have any kind of closed string insertions, but you have two boundaries. That's the annulus diagram. And so if you compute this annulus diagram, you look at this coupling, look at how they couple to the local functional, and you find this equation. That's the part of the quantum mass equation. And if you look at the del of this one, you degenerate into 3 diagrams. You want to solve this equation, and you see like this part together with this part is basically the BRT transformation on a potentially to be solved annulus. The right-hand side, there's one contribution from this guy. This is a one-loop anomaly, one-loop stuff from the open string sector, the gauge theory side. And the second term is basically the tree-level amplitude from closed string side. So it's just such a bracket. And this is familiar from the Green-Schwarz mechanism. And to solve, you want to solve this equation, you want the cancellation of these two. And in our case, I mean, if you compute these 2 diagrams explicitly, you will see like if you work with like a super Lie algebra GLN/n, they're gonna be canceled out explicitly. And just a very brute force calculation. And that's how we solve this problem. I mean, and I was trying to explain the solution like physically, I mean, in terms of the coupling constant. And then you can do an analog of open strings. I mean, type 1 version where you have a particular Z2 action and you look at a Z2 fixed point. It turns out like we have a very natural guess for the answer. So, for example, if you look at the Lie algebra of SON, it turns out that there's corresponding type 1 Kodaira-Spencer gravity. Sorry, there's a typo here. This corresponding type 1 Kodaira-Spencer gravity is given by such polyvectors where k plus m equals odd numbers. So this is a fixed point of the Z2 action. Such a thing can be coupled with like a SON, like Holomorphic Chern Simons, without anomaly in the following case. Actually, it's going to be coupled with like SON plus n/n. You can add, and the way we construct this coupling again is by couple this Holomorphic Chern Simons with such a Lie algebra in the larger limit to such a Kodaira-Spencer gravity, and we find the following result. We find, for example, on C3, it is only consistent if you couple to SO8 Holomorphic Chern Simons, and if you on C5. 10 dimension, that's the dimension we are interested in, and for this type 2B supergravity. And this is only consistent with the SO32. And that looks familiar from this string theory point of view, but we don't see the other groups like EA cross EA, so on, but we see these two groups naturally in this Holomorphic Chern Simons. And this matches with that of the type 1 topological string. And that's
Let me ask you.
Yes.
So first, what is T?
Oh, sorry, this T should be U in our previous notation. So that's the descendant. Yes.
Okay, so what, just remind, maybe I forgot, about X equals to C3. So it should be like a 6-dimensional theory.
Yes.
So what is this group SO8 here? So what is the theory? What is the special theory that you mentioned?
No, this means like this guy is given by the following, like this on C3 is you look at this the book complex valued in SO8 plus n/n.
Yes, of course, but I mean that we know SO32.
Yes.
It's just the heterotic string.
Yes.
So SO8 would mean that you have the 6-dimensional theory.
Yes.
It could be what I used to call small theory, like 25 years ago. And you see,
this is
okay, so n equals 8.
Yes.
So it means that there is some special SO8 gauge theory in dimension 6 that plays the role of SO32 in dimension 10.
Yes.
So what is the counterpart of this theory in the in so-called physics?
Mm-hmm. Well, we don't have a precise answer. For example, on C5, you know, this is we have basically the effect, the theory coming from this like a D9 brain, something like that. And on C3, on SO8, well, you can have a D brain there. I mean, to geometrically engineering this model, but we don't have a precise way to say such a thing is local is a twist of some stuff. For example, in 10 dimensions, we know like if you start with like a super Yang-Mills and do a twist, you end up with like Holomorphic Chern Simons. You can look at SO32, and on the C3, whether this is a twist of a particular physical model, or
Yes, exactly. It's my question.
I don't know, but
so my question was: do you have an idea of so-called physical model that brings to such gravity in dimension 6?
Well, I don't know precisely. This one for six dimension is not clear.
Because 6 dimension is very interesting dimension.
Yes.
If you if you compactify on the 4-dimensional instanton and you take a decoupling limit, you get a 6-dimensional theory. I mean, in so-called physics.
Yes.
However, I never heard about particular choice of the gauge group here. So people used to say that gravity is decoupling, and that's why you do not need to have anything. However, what you predict means that there is some hole in this argument, and there could be something like gravity in dimension 6, and there should be something distinguished in physics with exactly this gauge group.
Yes.
It is related to the following issue. People used to get this heterotic theory by compactifying of M theory on an interval. And people used to say how you get E8 times E8 on it. So it would be very interesting to find something in so-called physics here.
Yeah, I see.
So you are just not mentioning it. That's why I'm asking. Maybe I missed something. Okay.
Yeah, I don't know precisely. There's actually recent work by Brian Williams, also by Filson. They study twists of the 1,0 models, like in 6 dimensions, and some other stuff. And they appear to see. It seems like they started to see these components, like this type 1 polyvectors. But it's not. It's not clear yet precisely what it points to. So my answer to this question is like I don't know, but yes.
Okay, so you see, being a physicist, I cannot just let it pass by. Okay.
Yeah. Yes. I understand.
So it is something new, very new. Okay.
Yeah.
Unexpected. Okay.
Thank you. Yeah. Okay. I think that's. The way to prove this anomaly cancellation is, again, it's very similar to the physical way of computing this anomalies for the gauge group and so on. So that's basically all I want to explain. Thank you very much.
Thank you very much. Questions?
Siri, I have a question. Could you go back to the theorem slides in the last, the theorem slides? Yeah, previous two.
Yes.
Theorem, yes. Yeah. Yes. So the first question is that when you say holomorphic Chern Simons, so do you mean that in this path integral you need to integrate over all the gauge field on this?
Well, this theory is if you compute the cohomology, this theory is almost trivial because you see like it's on Cn. So the theory here is only non-trivial for local operators. That's something that mathematicians don't quite study much, because, for example, if you look at bundles on Cn, everything is trivial, and then you might think like, well, there's nothing happening here. But if you really look at local operators, they have interesting like operating expansions and algebraic structures living on the space, and that's the different content of the theorem. So you're asking like how, whether you integrate over everything, you get the modular space of vector bundles. But that one is trivial from this perspective because it's only CN, for example.
Right. So should I consider the gauge field dynamic here, or you actually use what do you say the operators to replace the definition which involve the dynamic gauge field? Is that?
Yeah. So here, so let me say it this way. Here, only the dynamics of the local operators are interesting. Probably this, yeah. So it's it doesn't lead to crazy stuff on this modular space. I mean, at zero modes that you might. I guess that's the question you have in mind.
Right. Yeah. So there's no more modular space. You mean
no,
the modular space? Okay.
It's not interesting for the modular. It's only interesting for the local operators and the algebra.
Okay. I see. Okay.
Yeah. So that's why it's a little bit like a strange from in the first place when I trying to give some like math talks on this stuff, like because you look at this copy, and I mean, it's just every bundle is trivial. So what it can say, but just like for example, if you look at a very interesting like even like say, you know, in this conformal field theory, you leave it on plane, you have a trivial. I mean, you have free theory like even like a beta gamma BC system. You have interesting operators. You got these vertex operators, and so on. And that's the local. That's the kind of thing that you don't. Well, eventually, if you compactify the theory, you will see the effect. But even you don't compactify, if you just study local stuff, you have interesting algebraic stuff in algebraic structures, and that's the kind of thing we are trying to understand, basically.
I see. Okay.
Yeah. So,
okay. Thank you.
Yeah.
Any other questions?
I have a question.
Yes, Andre.
I'm sorry. Actually, I have 6 questions.
6 questions. Okay. I mean, maybe
you see,
we can stop recording. Maybe you can ask later in that case, maybe.
So I have these questions here
Okay.
on the board.
Okay.
And I also have a board here.
Oh.
But I don't know the rules of your seminar.
Okay,
So,
then first I'll finish the recording, and you can ask the question if the time till Suli's time permits. Okay, so
I will follow instructions. Okay, so
okay, so first I will finish the recording, and then I will leave this space for informal discussion, so you can ask Suli more question. So thank you very much. So let's thank the speaker, the Suli again, whatever method. Okay, I will stop recording.